In this question, we're going to look at how to do a confidence interval for a single population proportion using Excel. So this question says, a drug is used to help prevent blood clots in certain patients. In clinical trials, among 4,536 patients treated with the drug, 188 developed the adverse reaction of nausea. Construct a 95% confidence interval for the proportion of adverse reactions. So the first thing we're asked to do is to find the best point estimate of the population proportion, which we denote by the letter P. So anytime you're doing a confidence interval, you're going to start by finding the point estimate. The point estimate is just the value that we get from the sample. That's the best way for us to start to get a prediction onto what the value for the whole population would be. So the point estimate is always just the statistic you get from the sample. So here, since we're looking for a population proportion, the point estimate will be the proportion that we got from the sample. And we can see here that in this sample, there was a total of 4,536 patients, and of them, 188 developed nausea. So the proportion is going to be 188 out of 4,536. And we can do that in Excel quickly using it like a calculator. Anytime we start a formula in Excel, we're going to start with an equal sign. So we can just type that 188 divided by 4,000, what was it now? Let's see, 4,536, 1,536. And once we're done typing, we go ahead and hit enter. And that'll give us the proportion value that we were looking for. Now notice that the decimal here is going out quite far, but my MATLAB only wanted us to go to 3 decimal places. So you can go ahead and have Excel change this to be showing you only the first 3 decimal places. As long as you're on the Home tab, you should see these 2 icons right here that will let you increase or decrease the number of numbers after the decimal point. So we're going to decrease this until we only have 3 numbers after the decimal point. So the point estimate, rounded to 3 decimal places, is 0.041. Next, we need to find the margin of error. So in Excel, there is no direct way to find the margin of error with a formula. So we're going to have to build this formula ourselves in Excel. There are other programs such as StatCrunch, StatDisk, and a lot of others that will find you the margin of error without quite as much work. But if you're using Excel, you need to do the formula for this one yourself. So there's going to be a few steps. First of all, I'm going to go ahead and label this point estimate that we found as P hat. P hat is the way we denote the point estimate. Or you could do it like this, P with a little hat on top. The next thing we need to find is the alpha value. So the alpha value is basically just the difference between 100% and the confidence level we want represented as a decimal. So in this particular problem, we were trying to get a 95% confidence level. So in Excel, to find the alpha value, we're going to start with an equal sign and do 1 minus 0.95. The 0.95 is because we have a 95% confidence interval. So we hit enter and we get 0.05. The next thing we need to do is find the alpha divided by 2. Why are we finding alpha divided by 2? If you look at this picture, which is in your textbook, this is kind of what we're looking for. So this middle section here that's denoted in yellow, that's the area where we are confident. We are going to be confident that the value of our population parameter is somewhere between this lower value here, whatever it is, and this upper value here. The areas here in the tails together are the value of alpha. So since these are symmetric and we have 2 of them, the area of each individual tail is alpha divided by 2. So we're going to figure out the area in those tails, just taking that alpha we found above. So I'm going to type an equal sign and then just click on the alpha above and then do divided by 2, enter. So the area in each of these 2 tails is going to be 0.25. So 0.25 is here, 0.25 is here, leaving 95% or 0.95 in the middle. Now that we have that, we need to find our critical value. So the critical value is a z-score. We denote it just like this, z alpha over 2. In this case, we're using a normal distribution, and we're trying to find this value right here, z alpha over 2. So that's the value here that separates the top 0.025 area from the bottom 0.975 area. 0.975 is a combination of 95 here plus another 0.025 here. So to do that, we're going to use the norm_in function. So we go to Formulas, More Functions, Statistical, all the way down until we see the norm_in function, norm_inv. Click on that. So the probability we want here, you can put in as 1 minus the alpha over 2 value. You can just click right on that value and it'll pull the number in. It has to be 1 minus that value. The mean is going to be 0 because we're talking about z-scores here, and the standard deviation is 1, again because we're talking about z-scores. So we're going to click OK. So now we have our critical value right here. Finally, to find the margin of error, we're going to put in this formula right here, z alpha over 2 times the square root of p hat times q hat divided by n. N is the size of the total sample. So we're going to start a formula. First, we're going to put the z alpha over 2. Remember, that's the critical value, so we click right here. Then we're going to do times, which is just the asterisk. To do square root, you can type SQRT and then open a set of parentheses. Now we want to do p hat. P hat was this number right here, so we can click on it and it'll pull in the p hat times. Now we want q hat. Remember, q hat is just 1 minus p hat. So we'll open a set of parentheses and do 1 minus p hat and close the parentheses. So now we have square root of p hat times q hat. Finally, we need to divide by n. Remember, n in this case, let's go check it out. That was the total value of the sample, or the total size of the sample, excuse me. So that was 4536. So, whoopsie daisy. So 4536 right there. Close the parentheses and hit enter. So this is our margin of error. This is our margin of error for this particular sample. So let's take a look at how many decimals we wanted. We wanted to round to 3 decimal places for this margin of error. So right now you can see we have 4. We're going to go back to the home page, come back here so we can change the number of decimals. Now we have 3 decimal places, so our margin of error is 0.006. Now we want to construct the confidence interval. You can see there's 2 values for the confidence interval, a smaller value and a larger value. We're trying to find an interval of numbers from a smaller value to a larger value, and we can say then that we are confident that the value of the population proportion is going to be between those 2 numbers. Now that we have the point estimate and the margin of error, calculating the 2 limits of the confidence interval is very easy. So we're going to have a lower limit and we're going to have an upper limit. Let me just make these a little different. Okay, so the lower limit is just going to be the p hat minus the margin of error. So we can start an equal sign to make that formula, and we choose p hat, which is this guy right here, and we subtract the margin of error, which is this guy right here, and we hit enter. So that is the value for the lower limit of our confidence interval. The upper limit is the same thing, but instead of a minus, it's going to be a plus. So equals p hat and then plus the margin of error right here. Enter. So these 2 guys, So these 2 guys right here are going to be the lower and upper limit of our confidence interval. Let's go ahead and check. We want 3 decimal places again. So these are already to 3 decimal places, which is nice. So we have 0.036 for the lower and 0.047 for the upper. Finally, we need to interpret this confidence interval. Remember, we had a 95% confidence interval here, and this was the interval we came up with. So the correct way to state this, where it says write the statement that correctly interprets the confidence interval. So the correct one is going to be letter A. we have 95% confidence that the interval that we just came up with from the lower bound to the upper bound actually does contain the true value of the population proportion.